General relativity, step by step. I've been talking about gauge transformations, which are small changes in your coordinate system and their effect on our equations. And in the previous screencast, I showed that the Riemann-Christoffel tensor does not change under gauge transformations. Well, of course, the Riemann tensor itself doesn't change, but what I showed was that the components of the Riemann-Christoffel tensor don't change under gauge transformations when we make this linear approximation. And indeed, in the previous screencast, I showed that the effect of a gauge transformation was to turn our h mu nu into this formula here, h mu nu minus di mu psi nu di nu psi mu. See the indices swap over there, where psi, this psi thing here, is the change in coordinates. What I'm going to do now is to consider what a gauge transformation does to h bar mu nu. That turns to what? Well, let's just write out the definition of h bar. That's just h mu nu, and then we subtracted a half eta mu nu, where that's the flat space metric, times what? Times the trace, which was the contracted trace like that. I'm going to rewrite that as, what am I going to rewrite it as? I'm going to rewrite it as g alpha beta times h alpha beta, summed of course over alpha beta. So under the gauge transformations, what do? Well, this one turns into h mu nu from this formula here, minus di mu psi nu, minus di nu psi mu. What does this guy turn into? Well, I need to do a little bit of algebra first, and then I'll take it over to the gauge transformation. I'm going to do a little bit of algebra first. So algebra turns this into minus a half eta mu nu. Because I'm only working to first order, again, I can replace this g here with an eta, which is just the, oh, it's gone off the screen, this flat space metric here, times h alpha beta. Now I can go over to a gauge transformation, which is minus a half gauge transformation, eta mu nu, eta alpha beta, times whatever it is that this goes to, which is h alpha beta minus terms like this, but with alpha and beta instead of mu and nu. Alpha, beta, di beta psi alpha. Whew. Right, now I need to do a little bit more algebra. It's minus a half eta mu nu times h, because this term here multiplied by that just gives me the trace of h, minus yes, what I want to do, there's different ways to do this, but what I'm going to do is I'm going to apply this. Oh, actually, I'm going to get my red pen out. Blue pen, what the hell. I'm going to sum that beta with this one here, and that beta there with this one here. No, I'm not. No, I'm not. I'm going to do the blue one first. Let's go back to black and do the blue one. We're back in black now. We have got di alpha psi alpha upstairs because the metric tensor has raised that index there. Minus, and now for this term, I'm going to get a different colour pen out. I'm going to get the grey. That one there is going to work on this thing here. Yes, that's right. So that's going to turn into, better go back to black, di beta psi beta, because the metric tensor there has raised that term there. Now here's the clever thing. Again, this is just a piece of magic. It speaks volumes as to how clever the summation convention is, and the linear approximation, and one's physical intuition. These two things here are the same term. So what we are left with is minus a half eta mu nu times h, That's that. Plus, because a minus times a minus is a plus, and we've got two things that are the same. We've got eta, because 2 halves are 1, eta mu nu times di alpha at least, xi alpha. Whew, that's nice. So what have we got? Oh, I can just do a little bit more simplification. That's going to be plus a half eta mu nu h bar plus eta mu nu times effectively the divergence of psi. So let me just write all that down. We've got these terms here and these terms here which have to be added. And that tells me that h bar mu nu goes to, under a gauge transformation, what it was before, minus di mu psi nu minus di nu psi mu from these terms here. Oh no, I keep on writing the di psi mu, which are these terms here. And now I've got a plus eta mu nu times the divergence of psi. Let me just write that out again. H bar mu nu goes to, under a gauge transformation, which is psi, which is small, what it was before, minus, I'm going to bracket it slightly differently, psi nu plus na psi, that's that term, this term, nu psi mu, plus flat space tensor mu nu times effectively the divergence of psi. That's quite nice. That means that I can start fooling around with this. I can start using that to try and simplify the Einstein field equations, which I'll do in the next screencast. But I'm worried I'm gonna cock it up if I stop. If I try to put too much into one screencast. So I'm going to stop here. Stop.